started.
All right, great. Thank you everyone for attending my talk. Today's topic will be real-time IoT analytics using Apache Pulsar. Let's see if we can get the presentation here. So just the standard forward-looking statements. Obviously, as part of a corporation Splunk, we can't guarantee everything shown here today is going to be available. So just common disclosure for that. So about myself. So I'm a principal software engineer at Splunk, formerly from Streamlio as well. We were part of the core team developing Pulsar and working on Pulsar development inside of Splunk. Also the author of Pulsar in Action, and prior to that, Practical Hive. I've contributed to these two Apache open source projects, and formerly I was a practice director at Hortonworks focusing on streaming technologies, including Kafka, NiFi, and Apache Storm. And I'm in the picture, I'm the guy on the left there. If anybody wants to know who the guy on the right is, they'll let you know. I'll be free to let you know who that is. So let's get started. Let's first talk about what IoT analytics is. Let's sort of put a boundary around what we're talking about. So it's not just about loading the sensor data into a data lake to create predictive analytic models. It requires the ability to ingest and aggregate and process an endless stream of data coming off a wide variety of sensor devices on the edge. You need to also take that information and render real-time decisions at the edge of the network to optimize operational performance or detect anomalies quickly. You need to know if something's going wrong in your system and react to it in near real time rather than seeing it after the fact, after doing a complete processing of the data. So what makes IoT analytics different from traditional analytics? These are just some of the highlights that I like to focus on. There's obviously multiple factors, but I sort of put it into these three boxes. You just have more data, tons and tons of data coming in constantly, time series data just coming in continuously. It's also more complex. There's more complexity involved in it. You have multiple analytic techniques that are involved, and the analytics are distributed across the edge as well. And then also there's the third factor of automation required. So not only do you have to collect the data and run reports on it, you also have to integrate with operational systems, business process management systems, and bidirectional communication. So the fact that you detect one of these anomalies or you detect something going on, you have to send that back up to the IoT infrastructure and react to it, actuate an actuator or some sort of sensor to turn things off once you detect it as well. So those are some of the highlights around what makes IoT analytics different. Some of the challenges with IoT analytics is that you're dealing with a machine-generated data consisting of discrete observations, temperatures, vibrations, pressures that are produced at very high rates. Just tons of data, high volume data. And what we really need to process it effectively is an architecture that allows you to quickly identify and react to anomalous events, among other things, and just reduce the volume of data that's transmitted back to the data lake or your eventual story to your processing. So in this talk, I'll present a solution based on Apache Pulsar functions that distributes that analytical processing out across all tiers of the IoT ingestion pipeline. So what do I mean by the IoT ingestion pipeline? Traditionally, it looks something like this. So there's different variations of this, but there's basically two concerns that we're looking at. The data transport, which is getting the data from the IoT devices down to your analytical platform here. And then once it's available to the analytical processing engine there, then the filtering, the aggregation, the analytics starts taking place. So in Seth's wonderful talk he gave this morning, you're processing events one by one, but it is at this particular layer between the messaging system and the real-time processing. So all the data is delivered, brought all the way into the infrastructure, and you perform the analytics, on event-based processing or batching, et cetera, across all that data at that layer. So that's what I mean by the traditional IoT ingestion pipeline. So why Pulsar for IoT analytics? There's really three key differentiators inside the technology that make this a fundamental shift in the way that we process data for IoT analytics. The first is the embedded lightweight computing framework, Pulsar functions. It allows you to process events on the brokers themselves as either as threads or as individual processes. And as you'll see, the brokers can be deployed on the edge because they are decoupled storage and serving layers, right? You don't have in Kafka or NiFi or similar processing engines, there's a requirement for a lot of disk or for state storage to be co-located with the serving layer of the brokers. And with the decoupling of those layers in Pulsar, that allows us to host those brokers up on the IoT gateway devices, and then we can do the processing there. A third factor that just came out is the support for the MQTT protocol directly. So it allows Pulsar to consume the messages directly from the MQTT clients and do the processing with Pulsar functions as you would any other sort of input framework as well. So when you combine all three of those together, it allows you to shift the processing of these events, these discrete events of IoT devices, up closer to the edge. And your Pulsar IoT data ingestion pipeline looks something like this, where you can see there's still a data transport layer involved, but the filtering and the aggregation can be done all the way up at the IoT gateway devices, right? Where if you can host Pulsar brokers with a small footprint of a few gigabytes of memory, even a gigabyte of memory, you can do a lot of processing there and perform the analytics much sooner and react to it much quicker in real time. It also allows you to filter the data, as we shall see later on, and not have to send the entire volume of the data downstream to do the processing and then react to it as well. So that's the fundamental shift that Pulsar allows us to do. So let's talk a little bit more about, just at a high level, talk about these different components. First would be the Apache Pulsar functions. I'm sure most of you are familiar with that. If those are not, just sort of summarize it here. It's a native stream processing. So it gives you a serverless computing framework, allows you to execute your own user-defined functions to process and transform data. It's a very simple method. It implements one method called process. And every time an event comes in, it gets executed. Your code that you write gets executed against it. This is very powerful because it allows you to leverage existing libraries, which I highlight there, to encode within, it's already written in Java, Python, Go. So all your favorite libraries, which we'll cover here and later on in the talk, are allowed to just bring them in just as a regular dependency. They enable different actions like dynamic filtering, transformation of data, dynamic routing of data, and also some analytics as well. And they can run anywhere a JVM can, which is including the edge devices, which I alluded to earlier, would be in those IoT gateway devices. So very, very powerful processing out on the edge. They come in three different sort of flavors. First is the stateless one, the record-based filtering and enrichment. So you can do things like lookup, range normalization, field extraction, scoring, basically things that don't involve any sort of state. So for example, 2 + 2 is always 4. We don't need to know any other state. When you give us 2 and 2 in the operator, we know that 4 is always the expected result. The second one is a stateful one. Again, cumulative aggregation or filtering. Again, if you want to count to 10, you have to know that you counted to 9. That was mentioned earlier. This is that sort of processing. So you can do things like counts, mins, max, averages, cumulative averages as well, using very stateful processors. And then also part of the framework are windowing-based aggregation. So you can do time-based windowing, count-based windowing as well. So you can count all the events that come in over the first 1 minute, or over the first 10 events, whatever, and do a moving average or pattern detection across those types of things. So there's 3 different ways of mechanisms of doing Pulsar functions that you can use for IoT analytics and as part of an overall framework. So that's sort of your base tools that you have to work with here. So now let's talk about a fourth tool I'm going to add using Pulsar functions that allow you to, using the Pulsar functions, you can implement distributed probabilistic analytics. So what does that mean? That's a mouthful there. So what does that actually mean? Sometimes it's sufficient just to provide an approximate value when it's impossible and practical to give a precise one. You forego a little bit of accuracy for exchange for real-time processing as well. So they can give you approximate values when the event stream is either too large to store in memory or the data is just moving too fast to process, right? You don't need to know down to the second how many IP requests have come into your particular server. You just need to know by order of magnitude of tens or hundreds or maybe thousands. That's what I mean by an approximation. You just need to have a rough idea of what you have. And that if you're willing to trade off that accuracy, then you can leverage algorithms that require only a few kilobytes of data, which again is great for an edge device where you need to be co-located with a lot of other different services, et cetera, and you have a very limited memory footprint as well. Central to all these probabilistic algorithms primarily is a concept known as data sketches. It's a common theme throughout all those different probabilistic data structures, and they're designed to require only enough data necessary to make an accurate estimation, right? Again, they're commonly implemented as bit arrays or maps, so therefore they only require kilobytes of data rather than megabytes or unbounded data structure you're trying to store the state in. Again, they're ideal for resource-constrained environments. And they only need to see each incoming data item once and are therefore ideal for processing infinite streams of data. They do not require you to go back and process data again to give you an average. You can just, once you've seen the data one time, that's sufficient for you to have an accurate calculation based on using the data sketch. So let's walk through an example to show you what I mean by a sketch, right? This is, in this case, the sketch is the stream of data is a pen drawing a picture. In real time, it's coming in bit by bit, point by point. I sped it up a bit to do it. But what you can see here is as the data comes in, you can determine what is actually being drawn before all the data arrives. And at some point, you have a clearer view, but your picture becomes clearer and clearer of what's going on in there. So really, you don't need all of that data to make an accurate decision of what you're going to do. You can just wait for at a certain point, you know that the data came in, right? So that's a visual representation of what I mean by a sketch. So what are some of the properties of data sketches, right? You have configurable accuracy. So you can size them ahead of time. Again, you pre-size them based on how big you want them to be, and that's directly inversely proportional to the size of the sketch is your error rate or your accuracy. For example, so if you want to be accurate to 3 decimal points or 4 or 5 or 6, you can quickly know ahead of time, okay, I need my sketch to be exactly this big. And when you allocate it in memory, that's all you have to do. And then you know exactly what your resource requirements are going to be. It's configured in advance, and you have everything there that you need to know. The other big value big benefit of using data sketches that allows non-additive operations to be additive. So what do I mean by that? Sketches can have the property where they can be merged into a single sketch without overcounting. So if you have a sketch, this allows your task to be parallelized and combined later. So you can run multiple parallel instances of your Pulsar functions to process all the data. Again, you have one function trying to consume all the data, it still might be overloaded. Pulsar functions allow you to be run in parallel. You could run 5 or 6 or 10 instances to consume all that data to keep up with the rate or the volume of data being generated. While at the same time, then later on when they each have their respective sketch, you can add those back together to give you a complete, accurate, and they would not lose accuracy adding those back together. So you can think of it like the MapReduce paradigm where you can sort of everybody does their task, and later then you can combine the results and they all work out just fine. This allows you to combine them across windows of execution as well. So the typical use case is you could store Quantile which is a type of sketch, every 5 minutes in your database, and you have that data. So for this particular sensor type, each Quantile will have a minimum, a maximum, and an average for that period. And if you query the database and get that particular Quantile, then you can get those values for that particular period. However, if you want to know what the minimum was, the maximum was over an hour period, for example, then you just simply need to grab those 12 sketches, those 12 Quantiles from the past hour, merge them all together in one operation, and then you can query the exact same way. What was the min over the hour? What was the max over that past hour? So it's very, very powerful, not only to process it in real time, but then when you later on to do analytics on it, you can go back and dynamically say what was over the last 1 hour, 5 hours, any sort of random period you want, and query the data as such. Now there's sketches there's a multiple what they call families of sketches, and I just sort of highlight them here and some of the different capabilities you can do. So I'm going to focus on a few, but this is what I demonstrate today is not by any means an exhaustive list, right? There's things like theta sketches, which do count distincts. So again, how many distinct IP addresses have come into our router over the past hour? You can do a tuple sketch, where it's basically logically equivalent to a group by. So you can say, how many people came in with this particular, these two particular attributes, and do an analysis on that. Quantile sketches, which I alluded to in the previous slide, is primarily used for anomaly detection. So you can sort of do a measurement of what the average minimum, maximum, and what each percentile of that particular data item, observed data, falls into. Is it considered anomalous or not? Is it a normal value as well? It's a self-learning sort of sketch. So you just feed it some data, some random events, and it will figure out, for example, what constitutes a normal value and what constitutes an abnormal value. Other sketches are like frequent items sketches, counting sketches, top 10 tweets, top 10 queries, top 10, items sold, things of that nature. And then obviously sampling, you can do a ratio. So you can get samplings of different data sets and do ratios, percentage of, what's the average of, ask these sort of answer those types of questions as well, all using these different sketches. So their use cases are quite broad. So now let's look into, basically to summarize, what are the Pulsar functions and data sketches give us really 7 big wins. First is the size of the query process, right? You don't have to store all the data. You can just query just a small subset of that. Big win number 2 is just the mergeability, which enables parallel processing, whether it's, you know, in the stream or later on when you're doing the analytics, you can combine the data sets later on and do it all in parallel. It simplifies the query speed because you're not scanning millions of records. You have a summary across a bitmap, which is a few kilobytes, so the results are almost instantaneous. But it makes the architecture quite simple because you can just have the data processed one time. There's no storage, there's no data cleansing, or there's no process of that matter. You simply observe the event, maintain the sketch, store the sketch, and evaluate it at a later time. It also enables real-time updates and late data arrival. So if you identify a piece of data comes in later on, you go back and find the window for that sketch. You can add it in, and it's completely fine. It just updates it, and you still have that data. So you don't have to worry about late data arrival with sketches. And then obviously resource utilization and cost, right? You have a smaller data structure. You need less data to host it. You send less data down the network in the data collection process. So it's all 7 big wins that you get from using these particular combination of technologies. Right, so obviously you combine those two together, it's a perfect fit for IoT analytics because both work well in resource-constrained environments like the edge. Both are designed to process infinite streams of data without retaining it. There's an existing Apache license library, which I linked here, of all the major sketch algorithms available that can be easily integrated in your Pulsar functions. Again, you just include that library in your POM file or whatever your build tool you want for Java, and it will automatically just have access to those, right? And it's been written in conjunction with 7 different PhDs, individual PhDs in mathematics. You don't have to worry about if the accuracy of that data. You don't have to rewrite it and try and implement it yourself. It's not an algorithm out there that you have to try and rewrite yourself. It's already there. It's prepackaged, tested, ready to go, validated, peer-reviewed papers written on it. It's really solid. You don't have to worry about that. And it also allows us to drastically reduce the volume of data sent back to the data center for storage and processing. This saves time and money, right? In the previous, if you remember earlier, I showed you the traditional approach of the IoT pipeline where you're sending all the data. So if you have hundreds of millions of events, they have to get transported all the way through the messaging system in order to be available to the real-time processing engine in order to do the analytics. The data volume of that could be in the tens of terabytes. That all costs money to store, infrastructure to host it, network costs to send it over, data latency to send the data across, and then ultimately run your processing and then come up with a solution or your analytics, your result. Using the data sketch approach, what we do is we still have the same hundreds of millions of events, but the IoT gateway there compresses it with the sketch by creating a summary. It takes those hundreds of millions of events and condenses them down to small kilobyte-sized sketches, which can then be sent down the data collection pipeline and access to give you approximation values. So the data transport cost and the latency is reduced, dramatically. It's collapsed by a factor of maybe 1,000 to only tens of gigabytes. This allows you to have a much more cost-efficient and more real-time analytics approach. So enough of the preliminary stuff. Let's get into some actual sketchy functions here. Let's look at the first one would be something like event frequency. So a common statistic you want to compute is a frequency at which an element occurs. Like basically answer how many times has element X occurred in this data stream? How many times do I see this IP address? How many times has this person attempted to log into my network, etc. So you just want to if you're trying to analyze all that data for a single industrial plant, millions of readings per second, there just isn't enough time to perform the calculations and store that data, right? You'd have to store hundreds of millions of events, and if you wanted to go back and answer that question, you'd have to scan those events from a database or an event processing tool, and then come up with that result, right? In such a scenario, you could choose to forego an exact answer, which you probably would never be able to compute in time, in exchange for an approximate answer, right? With an acceptable range of accuracy. Again, back to, I need to know exactly how many users I've had or how many IP addresses. I just need to know by the magnitude of hundreds or thousands, etc. Underneath the covers, that uses what's called a count min sketch. So this is the one algorithm slide. I guarantee not to bore you with this. Basically, it comes down to an M by K bitmap. And so an element comes in, it's run through a series of H individual hashes, which create different values. And every one of those values is then mapped to an element in that bitmap, and you increment it each individual time. So what that does is allow you to basically force an imprint. Think of it as like bingo, and you're stomping an individual marker on that thing. Every time you add a sketch to that, it becomes greater and greater impressed. So later on, when you want to get an approximate count for those, you just basically scan all those elements. You run that hash again, say, okay, how many times have I seen this? You hash it again. You go back and look where those individual plus ones would have been placed, and you take the smallest of those. That guarantees that you were at least that many times, because you're guaranteed to have impressed it at least that many times. Now, there could have been other ones that added to that, but you're guaranteed that that's your minimum. You have seen it at least that many times, which is why it's called the count minimum. I've seen it at least this many times. So this is all the code, the Pulsar function, to do something like that, right? Every single time you create the sketch. It's obviously, this is somewhat pseudocode. Obviously, don't try to run this at home. But every time the process event comes in, assume you get a long value. All you do is update that. You add it to the sketch, and then at any point in time, you can go back and get an estimate to say, okay, how many times have I seen this one in the past, right? And then based on that logic, you get an estimate real time. You can react to it. Say, okay, I've seen this one, 100 times in the past minute. Maybe that becomes problematic, and you can react to it. So that's basically 5 lines of code to do all that different processing. Keep an accurate count, and later on you can send it down to the database for storage. A second sort of sketch would be frequent distinct tuples. So this is a use case where, let's say you have a stream of pairs of IP addresses and user IDs, and you want to identify the IP addresses that have the most different user IDs, right? Who's trying to spoof you? Who is really trying to come in from the same IP and pose as 5, 10, 15, 20 different user IDs, right? Who's doing this, right? So theoretically, if you have a stream of 160 items, let's say, and each have 4 different types, then the distribution should be equally, and what's equal, then each item should appear 40 times, right? But the most frequent items within the tuple is any of those that consume more than their fair of the threshold of occurrences, right? So back to an even distribution, each IP address should have 1 or 2. So over 160 items, you expect everyone to have 1. This is going to bubble those up. The ones that have a high number, a much more frequent occurrence of having distinct values in there. That's the basic approach to distinct tuples. Again, leaning on the library quite heavily. The way to do that is quite simple. You create the sketch within there, and I would definitely say refer to the documentation of what these individual parameters mean when you're constructing it. But basically, it has to deal with the volume and the accuracy of how accurate you want the sketch to be. And then when an IP pair comes in, you basically just add that value. You strip out the IP address and the user ID, you add it to the sketch, and then later on you decide, okay, you can take that data and just go through it. I'm just showing here that you would iterate through those and say, okay, who are my top ones, right? After a minute, you could say, get these values, and in this case, I just iterate through to show you what they are, but you could react to those, right? Who are my top 5 IP addresses, and then react to those. Do whatever you need to do based on that, because the data's there. The key is that sketch is there in your memory. So in your function, whenever you query it, you can react to that. You can make decisions out there at the edge based on what you've seen in the past. The third and final one I'm going to cover is anomaly detection, and that's based on Quantiles. So most anomaly detectors have like a manually configured threshold that's not adaptive to even simple patterns. So instead of using a single static variable, like send me an alert when the temperature gauge goes over 100 degrees Fahrenheit, for example, you can use something like Quantiles instead. So most of us are familiar with Quantiles, and basically in statistics and probability, there's things like percentiles, for example. So the top 50% of all people are in the first, and then the next distributions, the top 75% are in the top 4, et cetera, becomes basically skewed out, and things that are really in the 99th percentile are considered exceptional or anomalous, right? For whatever reason, based on that data set. And it's independent of what the underlying values are. It's just the fact that based on the distribution of the data, a much smaller percentages should be in this range versus that range. We expect most of the values to be in the first 2 quantiles, and the last ones are exceptional. So there's a data structure known as T-Digest that was developed by Ted Dunning as a way to accurately estimate extreme quantiles for very large data sets. And it makes it particularly useful for calculating quantiles to be used as a good threshold for that. So the advantage of this approach is that the threshold is automatically adapts to the data set as it collects more data. As I mentioned earlier, you get a data set coming in, you're getting discrete values coming in from a temperature sensor, and that gets fed in. So it's continuously, it gets a ton of values at 58 degrees Fahrenheit, let's say, then that becomes sort of what is considered a normal operation. And then all of a sudden you see something that says 90 degrees, based on the quantile distribution, say, hey, that's not a normal value at all. We know that that's not normal based on what we've seen. That becomes an anomaly automatically. So it's been self-trained by the data to know what is a reasonable value and what is not. And so here's again, a real simple example, a few lines of code where you can throw this in a Pulsar function, include the library, and do something like this, right? So you have an update double sketch. You just create it. Again, you can size it based on how big you want it to be. Every time the metric comes in, you just grab it and you add it to the sketch. And then at any time you want, you can query it and figure out what quantile that value falls into. And if it exceeds a threshold, then you can publish to an alert topic, do some sort of action, right? Turn on an accentuator and do whatever you sort of want. But you have that, again, you have the data set there. You collect the data, you manage the quantile, and then you can query it based on does that exceed the threshold in real time on the edge. There's no need to send the data all the way back in order to make that sort of decision. You see it right there in real time. You have the complete data set. So let's sort of walk through what a high-level IoT analytics pipeline would be if you were to use Pulsar functions for that. And this is just sort of a hypothetical use case. But I want to demonstrate all the different ways in which you would use the Pulsar functions, right? So let's say your use case is to identify real-time energy consumption patterns, right? There's a network of smart grids that enable utility companies to gain visibility into how their customers are using it in real time, right? You want to increase and decrease energy generation to meet the demand, real time. You want to overproduce energy, and then that doesn't get consumed. That ends up being a lost cost. You want to have too little data and have some sort of rolling brownout. So you want to sort of adjust it, get it just right. You can also implement dynamic notification to encourage consumers or smart meters where they can automatically turn down your thermostat during peak periods, right? So people who opt in to say, hey, you can dynamically adjust my thermostat during the day. You would only do that, for example, if there were peak demands, and you would identify those people and do that. You can also perform real-time revenue forecasts, right? You can look at the real-time, how much energy has been consumed in real time, and you have a real-time revenue forecast based on what these bills are going to be, what they were metered at the meter, so you know what the bills are going to be. And another benefit is you can identify faulty meters and schedule maintenance calls to repair them. So rather than have people go around just randomly checking the meters, based on when you see this data coming in and bad values, you can automatically schedule updates and repair people go out and update those sensors, right? So it looks sort of like this. Again, apologize my crudeness, but each one of these boxes with a little Pulsar logo indicates what would be a distinct Pulsar function that performs a particular application or particular function on the data itself. So on the left, the meter, those are the smart meters, and the readers coming in a proprietary binary format. We'd have a function that decodes it. And if there was any errors, that becomes, you start adding an count distinct by meter ID. So that was the count distinct sketch. And you could identify those top offenders for, remediation and maintenance. Again, once you have a valid meter reading, then you could basically validate, okay, am I getting an actual value, right? Is the voltage consumed makes sense for this particular use case, right? Are they saying it's within the anomaly detection of this is a good one, this is a bad one. If it's a way out of, it's an anomalous detection, you may want to add that to the occurrences as well to say, hey, we might just be getting bad meter readings from this meter. Once you validated the meter reading and think it's good, then you can do some sort of lookup based on the meter ID, do some enrichment to figure out what location he's at, what customer ID they are. And then you can bifurcate that and do two ways for anomaly detection based on consumption, customer segmentation, or you can also do the aggregation and roll up all the meter consumption across the last 5 minutes, 10 minutes, et cetera. And then within that, across the location, you can find the top K users for that opt-in of turning their data consumption down as well. So that's the overall flow, and just the real simple. You can do it in like a handful of, 2, 4, like 6 or 7 different Pulsar functions. You can get all those capabilities, right? So let's sort of walk through this, how it would be done, function by function, again, using a bit of pseudocode. So again, the data comes in, it's a binary format. You just have a decoder right there that processes it. It takes the prototype, parsing of that data from the expected type. And if there's any sort of value, any sort of errors from that, then you publish it to the bad reading topic, right? In there, you'd have a function waiting to see, hey, it comes in. So you have your sketch, you do the count min sketch, you add it to that guy, you create the estimate of that one. And if he's above a certain value, you can say, hey, these are my top occurrences by meter ID. Once assuming you have a valid code instead, then you can sort of look at that value and say, okay, is this voltage exceed a certain, is it less than 0, for example? Is it anomalous, et cetera? That's a bad reading, right? So that also another indication that might be a faulty meter. Again, you update those occurrences as well. You publish back to that topic, hey, this is the meter, it's having a problem. It updates that min sketch again, so you have 2 bad readings for that guy, so on and so forth. Assuming that he passes it, then you actually have realistic data with some metadata on it that you can process, things like serial numbers, a time on it, a voltage, et cetera. And you can do some real-time lookups using Pulsar, right? So what is my, go get the location based on the serial number, go look at the company ID, if it's a company ID based on the serial number. And so now I've enriched that raw data with some additional metadata that I can use to do some evaluation on it as well. Once you take that rich data out there. So again, in this case, we have like a location ID, we have a company ID, and we can look at customer segmentation, right? So in this case, it did real simple, but it gives you an idea of, okay, small, medium, and large, right? So anomalous detection, downstream, we know that we're going to publish events to an anomaly detector, but you don't want to have somebody, a major industrial meter reading intermixed with a residential reader reading, right? What I use in my own home as far as energy in any given minute is not the same as a casino on the Las Vegas Strip with thousands of lights and neon lights, right? Those are already going to be anomalies. So we have to segregate those out and publish into different topics so that we can run them through individual anomaly detectors. On the bottom, we just take that enriched meter data and we take that voltage itself and we can just sort of add each one of those to the grouping by the location first, and then add in that energy consumption. And that just becomes a very additive. That's the aggregation I mentioned way earlier. You can keep the last 5 minutes of aggregation, do a roll up with a stateful function, retain that data, and then when you're done, you can publish it directly to the database because you've done, this is all our meter readings over the past 5 minutes for that. Once we've left so going on the top path, if you were to leave the customer segmentation topic and it decides, okay, again, we have 3 buckets, in this case, small, medium, and large. Again, you want to have your own anomaly detector for each one of those because the values are going to be quite different. So in this case, we have, each one has their own quantile, they each have their own threshold. You add it up and you maintain 3 separate quantiles based on the customer segments, and you can identify those ones that are high volume users, or something's going on within their sensors, and you may want to react to that as well. Once you've, and at the bottom, if you go back down again, this sort of jumps off path, but if you go down to the rolling energy consumption window after you left the content enrichment and we've summarized the data, we want to roll it up by location, right? So you have different grids across your individual city. You want to identify those top users by location. Again, this is how you would do it using the anomaly detection. Identify those ones. So for each individual group, what are the top 5 users for that guy? And you may want to post a list of, this is a bad offenders or people, or you may want to send alerts to say, hey, your energy consumption is high, or what's going on, or maybe, again, if you have control of their infrastructure, their smart home, you can sort of dial them down a bit because something's going on. And then that's typically abnormal for them. So let's just summarize what we've covered. I know we're getting close to the end. So IoT analytics is an extremely complex problem. And Apache Pulsar provides a platform for implementing distributed analytics on the edge, right? So the solution is probabilistic algorithms, and Pulsar Edge deployment allows you to solve some of that complexity there in the middle box of some of the challenges. That makes it much more easy to do IoT analytics, right? It allows you to leverage existing probabilistic analysis techniques if you're willing to trade off for accuracy as well. And allows you to act on your business in real time and keep the data local and minimize the amount of data you have to send back to the infrastructure to do the processing. There's some additional resources here as well. So again, I have some of the examples on my personal GitHub account. They're associated with the Pulsar in Action book that I'm writing. Again, I'm going to do this same shameless plug of this is my book if you were interested in purchasing it. There's also a 40% discount available for this. Not only this, but all manning material. So if you had something you wanted to buy, go ahead and use that code there to get your 40% discount. The Apache website for Pulsar, and then the Apache Slack channel. I'm on there quite a bit, answering questions as well. So those are where you get the additional resources. And with that, any additional questions? I'll check the Q&A at this point. I don't know if I have any of those. If I can see where the questions are on this. So we're in Q&A. So are there any questions? There's a Q&A.
It looks quiet in the Q&A, but I did get a couple that came in directly. I'm just going to add them in the chat if you want to.
Okay.
Hold on a second. Or I could just read it to you. It's not letting me add it. It says, how do you get data from the IoT devices to Pulsar?
So there's an MQT. That's a great question. There's an MQTT plugin now that was recently released, so you can add it, embed that into a Pulsar broker deployment on the edge, and it will open an MQTT port, and so those devices can communicate directly, publish directly to Pulsar over the MQTT protocol. Yep.
Awesome. Let me see. I have another one here. It is, what is the value of doing analytics on the edge versus in the cloud?
So I would definitely say the reaction to the event closer to the source, closer to the time it occurred is the primary value in that. And so again, reacting to event, there's business value closer to when the event occurred. For somebody who isn't putting something in their shopping cart, they took it out of their shopping cart. If you can see it and react to it in the cloud while they did it and offer them, let's say, just like a discount or something, hey, don't leave just yet, we'll give you a $5 off coupon, they can make that purchase while they're still on the website, still engaged. If you do it on the cloud, not only do you, again, you send all the data back, but then by the time you run your processing on that and sift through all that data and then not making that sort of decision, you still have to propagate it back up to the edge. And by that time, you could have lost that customer that could have left the site and you lost the opportunity. So again, it's the timeliness of the data, and the value of the data decreases over time. So reaction in real time is the real big value, I think.
Got it. Thank you so much for that. Mm-hmm. It looks like we have another one that just came in through Q&A. Can you see it, or do you want me to read it?
Yeah. Let's see here. Open. Can we control producer inside Pulsar function, like to create a router function? It creates lots of ephemeral topics per one. Is that it?
Yeah. That looks like it might be from earlier, actually. It just popped up.
Yeah.
But there's another one that just came in that I think is relevant to this.
How to get data back to the devices from the back end. So, yeah. So again, in that framework, you have the MQTT connector, so you can have the devices publish over MQTT directly to the Pulsar broker that's hosted on an IoT edge device. Again, it's a small footprint, but it is a fully functional Pulsar broker. And then since you have a decoupled storage layer, a bookkeeper, those topics, when it gets persisted, will automatically get published over HTTP down to your remotely hosted brokers in the cloud itself, or bookies in the cloud itself. And then from there, you can access it, those same topics over HTTP that were published to by MQTT. And so the data is, the transport layer is HTTP to the bookies, and you can have another Pulsar broker, because again, you can have multiple brokers running inside the cloud or on the back end and access that same topic data as you would normally. Yep, great question.
Cool. All right, we're almost at time, but I have one more that came in. If we have a couple more minutes, we can go ahead and take it. It says, what other use cases can benefit from this?
I would say just about any sort of processing on the edge, right? I mean, I'm still looking at ways that you can deploy more complex models out there. any sort of adaptive, not only IoT, but again, recommendation systems, if you're doing website analysis, any sort of security or distributed denial of attack. Cybersecurity is another use case that this could apply to, in additional to the industrial IoT space. So really anything where you have data being generated far away and you don't want to pay the price or the cost of having to ship that data up to the cloud to do your analytics and then make a decision and ship it back down to where you react to it and respond to that, I would say those are good use cases for that, right?
Great, thank you so much for that.
Yep.
We are just perfect on time right now, so we'll give people like a minute if they want. Anyone on the call, last minute question while we still have David here, let us know. But otherwise, David, just want to thank you again for this presentation today.
Yep.
Really enjoyed it and enjoyed meeting you. So
likewise, thank you. Thank you everyone
thank
for
you.
attending. Yeah.